So now we're going to take a moment and we're going to talk about aqueous solutions and strong and weak electrolytes. Now I can tell you to go ahead and recall that parts of the solution, the solute and the solvent. Make sure that you understand what each of those are. But the reason why we're talking about this is that we're going to talk about electrical conductivity, and that is the ability of a solution to conduct an electric current. Now, electric currents are nothing more than the movement of electrons. And so if we have ions who are free or want to give or receive different amounts of electrons, when those electrons are being transferred, we can have electrical conductivity. That's why salt water conducts electricity. Now, there are different couple types of electrolytes. We have strong electrolytes. Those are the solutions that are efficient at conducting electricity. And we have weak electrolytes that are only can conduct a small current. And we can test for this. I have a light bulb on an electrode. If I put the electrode in a salt solution, which is a strong electrolyte, we will end up with the light bulb being lit. If I put it in with a weak electrolyte, such as vinegar, it'll only be dimly lit. There are also things called non-electrolytes. Sugar would be a good example. But remember, it's because sugar, when it dissolves, is not actually broken into ions. It's just individual sugar molecules. So they cannot make electrons flow across them because they're not ions. They don't have electrons to donate or receive. So non-electrolytes do not allow a current to flow. Now, Svante Arrhenius, and I love saying his name, came to the conclusion that the ions in the solution create conductivity. Now, we're going to talk about Svante a little bit more as we go along, but he understood that in order to have electrical conductivity, you have to have ions. So let's talk a little bit more specifically about strong electrolytes. In this class, we're going to concern ourselves mostly with strong acids. Now, strong acids are considered strong acids because they are completely ionized, or what we call dissociated, when they are dissolved in water. In other words, they break into their constituent ions. Now, strong acids are those acids that, when placed in water, are said to be completely dissociated or ionized. There's such a thing as an Arrhenius acid, thanks to Svante. And he says that you can recognize an acid really easily. If it has an H plus ion when it's in water, it's an acid. So anytime we have H and then something, it's an acid. They're not all strong acids, but they are all acids. So earlier in the year, I asked you to memorize some strong acids. There was a fourth one, H3PO4. We're not going to concern ourselves with him too much. He's a little odd because he's what we call triprotic, meaning it has 3 hydrogens. So we're not going to deal with him. But you should know is that these are strong acids because HCl likes to break apart into H plus and Cl minus. HNO3, or nitric acid, likes to break apart into H plus and NO3 minus. Sulfuric acid likes to break apart into 2 H pluses, it's diprotic, and SO4 minus 2 ions. And so those are the ions that are present when they're dissolved in water. It's not like alcohol that stays together in a molecule. The molecules are just very small. These actually break apart into ions. Now, likewise, we can also have strong bases, and strong bases can have a very similar effect as strong acids when dissolved in water. These are ionic compounds containing the hydroxide ion, OH minus. The ones that you're going to deal with in here are NaOH, which breaks apart, of course, into sodium ions and hydroxide ions, and potassium hydroxide, which breaks apart into K plus and OH minus ions. And the reason why you deal with these most is that with the larger atoms, such as magnesium, calcium, things like that, hydroxides tend to not be soluble in water. They get a little cloudy when they're put in water, and so we'd like to use sodium, potassium, because those are the stronger bases. They completely dissociate. Now, on the other end of the spectrum, there are weak electrolytes. We have weak acids. They dissociate only a small degree in water, or ionize only a small degree in water. Acetic acid would be a perfect example. Acetic acid, when it's 3% in water, is called vinegar. It does conduct a small amount of electricity, but it doesn't completely break apart. And that makes our math a little more difficult once you get into AP chemistry and those types of things. We also have weak bases, and there's tons of weak bases, but ammonia is the most common one. That's the one that you use to clean your house. It does dissolve a little bit, but not perfectly. And then, as we said before, we have non-electrolytes, which are substances that dissolve in water but do not produce ion. So things like sugar. So understanding solubility and what will dissolve and what won't dissolve is very important, because if something does not dissolve and create ions, it cannot react. And so we need those ions in order for reactions to occur. And that's why we need to spend a lot of time here talking about solubility and those types of concepts.